So today we'll have 6 talks in the session. These are 5-minute talk, and then we'll have time for questions to the speakers. Please don't hesitate to ask your question over the chat.icr.org. So the first presentation today is about highly efficient architecture of new Hope-NIST on FPGA using low complexity NTT and inverse NTT. And then Zhang is going to give the talk. Nang, can you share your screen?
Okay. Is it okay? Can you hear me?
That's perfect. Please, you can start.
Okay, thank you for the introduction. Hey everyone. PQC algorithms are required to resist quantum attacks. And new Hope-NIST is such a lattice-based PQC algorithms for key encapsulation mechanism. NIST started computation for the PQC standardization, and New Hope survived the second round, but didn't make it into the third round months ago. But the introduced low complexity NTT and INTT can be utilized by some other candidates in the PQC algorithms and some fully homomorphic encryption schemes, such as Crystal DD-SERM, Falcon, Q-Tesla, LTV, and BFV. The special parameters of New Hope make the polynomial multiplication can be evaluated with lective rapid convolution. This method avoids doubling the size of NTT and INTT and the explicit reduction by the modular polynomial. But it requires pre-processing in NTT and post-processing in INTT. In NTT and INTT, FLT requires half n times log n modular multiplications, and pre-processing requires n modular multiplications, where the post-processing requires double n modular multiplications. The cost of the pre-processing and the post-processing is considerable when the size n is not big enough. The smaller the value of n, the higher the proportion of the pre-processing and the post-processing. As a result, we introduce the low complexity NTT and INTT to eliminate the pre-processing and the post-processing. The low complexity NTT merges the pre-processing into the DIT FFT by merely changing the value of the pre-computed Twitter factors. The computational complexity is reduced by n. This method has low additional timing cost or hardware resource cost. The low complexity INTT merges all the post-processing into the DIF FFT by changing the value of the pre-computed Twitter factors and slightly modifying the butterfly unit. The computational complexity is reduced by double n. This method has low additional timing cost in our hardware architecture, and the hardware resource cost is very small. In addition to the low complexity NTT and INTT, we propose low complexity modular multiplication for the modulus in New Hope. This modulus has a special property like this. We recursively use this property to reduce the product result. This is the architecture of the modular multiplication. Only one multiplication is required to generate the product. No additional multiplication is required for the reduction, because there is low if else or where statement. This method is time constant. This is the architecture of the low complexity NTT and INTT. It uses 2 butterfly units and a multi-bank memory. Among the NTT size with the same point size and the same modulus, our architecture is the fastest and has the smallest area time product. This is the architecture of the new Hope-NIST. It supports all the functions of key generation, encryption, and decryption. It uses double the bandwidth matching and time hiding to reduce clock cycles. The hardware resources are small, especially the IoT and the DSP. Our design is at least 2.5 times faster, and the ATPs are at least 4.9 times smaller than other new Hope-NIST designs on similar devices. And that's all. Thanks for listening. Any question?
Well, thank you very much for the presentation. I don't see any questions in the chat, so I will just start with two questions that I had. So on, I think, slide 2, you mentioned that, well, unfortunately, New Hope isn't anymore in the competition, but that the architecture can still be used for, I think you mentioned dilithium and QTesla and Falcon. I mean, that I believe that that's totally correct, but was there a reason to, for example, not mention Kyber or Saber or Entru Prime?
Well, because we use a low complexity NTT and INTT. They are used in the modular multiplications. There are some prerequisites. First, the modular polynomial should be x to the power n plus 1, and the second, the modulus should be a prime, and the primitive double nth root of a unit should exist. Third, the n should be power of 2. In Saber, because the modulus is power 2, it's not prime, so our method cannot be used in it. Actually, NTT cannot be used in Saber, but in Kyber, in the first round, our method can be used, but in the second round, Kyber changed the parameters, so the double nth root of unit don't exist,
Yep.
and so our method can't be used in Kyber.
Okay. So there was a question saying if it can be applied to the modular Q equals 3329 that is used in Kyber, but then you said, well, at least not straightforwardly, right? So that was a question that just appeared in the chat. Well, I don't know, Tonka, do you have any questions? Otherwise, I have one more.
I do have a question, actually. During the inverse entity, you're dividing by 2 on every, at every level. Is there a reason to divide by 2 all the time rather than divide by n, the power of 2 at the end of the inverse entity?
Well, well, the entity we first okay, let's see the definition of entity is similar to the definition of entity. For endpoint entity or entity, they are first split into 2 half endpoint entity or entity, and then we recursively split the entity to half and half again until until 2 point. And the difference of entity and entity is especially there is in the butterfly of entity there is multiplication by a half. The reason is that after entity there is there is a scaling by n is power of 2. So we merge this scaling into the FLT. So there there is after each butterfly there is a half.
Okay, thank you very much. Is there any other question?
Further question? I think so. There is now one question popping up in the chat here, asking if it could be applied to the Stockholm butterfly as well. Maybe we postpone this question and see if we still have more time for discussion at the end of the session and continue with the next talk, because we're already slightly over time.
Yes, so thank you very much for this presentation. We're gonna go now to the next presentation of the session. That is parameterized hardware accelerator for lattice-based cryptography and their application to the hardware software co-design of QTesla. And Wen Wang is going to give the talk. So up to you.
Okay. Hi, everyone. Can you see my screen clearly and hear me also?
Yeah. Yes, that's perfect. Thank you.
So hi, everyone. Thanks for attending this short summary session. I will give you a very high-level view about our work, which is parameterized hardware accelerators for lattice-based cryptography, as well as the application of these accelerators to a software hardware co-design for QTesla. My name is Wen. I am a final year PhD student from Yale University. This is joint work with my collaborators, Shan Quantian and Jakob Scheffer from Yale, Bernhard Jung from Mentrank in Germany, Nina Bingda from University of Waterloo, as well as Patrick Longa from Microsoft Research. So first of all, let's take a look at the new lattice-based hardware design that we have in mind. The idea for our design is to first develop a set of hardware accelerators that are generic enough to be able to support different lattice-based schemes. Further, we want to make sure that we have enough flexibility in our design, which means as a user, I can not only tune the design based on the security parameters, but further, I can tune the performance parameters when I target different applications. Another very important design decision we made in our work is that we use standard handshaking protocol throughout our design to make sure that the accelerators, as well as the whole software hardware co-design, can be ported easily among different standard processor platforms, for example, RISC-V-based or ARM-based processors. In our work, we used QTesla to showcase the performance of the hardware accelerators, and we basically provided a software hardware co-design for this digital signature scheme. QTesla itself is a second round submission in the NIST PQC standardization process. However, it didn't make to the third round. The property that makes QTesla stand out from the rest is that it comes with privily secure instantiation. This leads, however, to really large security parameters, as you can see from the table here. So in this work, a very important research question for us to answer is that how much the performance of QTesla can be improved by use of hardware acceleration. So to better accelerate lattice-based schemes, we provided a list of hardware accelerators, including a unified core for both shake and C-shake, targeting 128, as well as 256-bit security level, which means you can just take our unified core, it can offer you 4 functionalities. Further, we also provided a fully parameterized binary search CDD-based Gaussian sampler, as well as a fully pipelined NTT-based polynomial multiplier. And to fully accelerate QTesla based on our software hardware co-design evaluation results, we also implemented a sparse polynomial multiplier, which is parameterized, as well as a very lightweight HMAX sum module. So today I would briefly talk about the CDT and the multiplier design. This diagram here shows the high-level structure for the CDT-based Gaussian sampler. A very important design decision we made here, as I mentioned briefly, is that the communications between all the submodules within the sampler, for example, the C-check module, the PRNGs, the FIFOs, the binary search engines, etc. All of these communications, as well as the communications between the sampler and the outside world, are all implemented following XC4 like handshake protocol. In the end, we provided a CDT sampler, which is fully parameterized in terms of the 3 security parameters. You can further choose how many samples you want to generate at a time. You can regard it as your performance parameter, for example. And of course, the CDT sampler should be constant time. And the design in the end turns out to be very lightweight. You can find more of the evaluation results in our paper. So now let's take a look at the block diagram for the NTT-based polynomial multiplier. In our design, I think some of the other work from just 2020 also mentioned similar optimizations. Basically, we just need one unified core for both forward and inverse entity. And this is achieved by designing a unified butterfly unit for both the CT and GS butterflies. In the end, we provided a fully pipelined polynomial multiplier. And of course, it's constant time. And similarly, we support standard interface as we supported in the sampler. So now let's take a look at the prototype of QTesla on a RISC-V-based platform. Here on the left side, you can see there is a workstation, which is able to program the FPGA, load the compiled software, and do the data exchange through the UART interface. On the right side, we have an RTX 7 FPGA, which would run the SoC, which is the open source Morex SoC, plus the hardware accelerators that we developed. Okay, now let me show you some of the performance results for QTesla under different design configurations. The leftmost column, you can see different design configurations. Here, a plus sign means you can very modularly add a hardware accelerator into the SoC. For example, you can just add one accelerator into the design, or you can add several, or even all of them, depending on your area budget. We can see that when all the available hardware accelerators are added to the design, the best speedup is achieved for both the P1 and P3 variants. For example, for the P3 variants, when you add all the hardware accelerators to the SoC, you can easily achieve an over 100 times speedup. And of course, as expected, this configuration also gives you the best time error product. You can observe similar patterns for the signing operation, similarly for the verification operations. So that's pretty much it about our work. To know more about the details as well as the other accelerators, please check out our paper. And our project is also fully open sourced. You can already download the code from this link. And also I have a few other work about PQC on real hardware, including lattice-based, hash-based, and very soon in the future, s-22-based. You can also check out our link for the other work. Thank you for your attention.
Thank you very much. And just as before, I don't see any questions in the chat yet. So, so I will start with I have two questions. So yeah. Maybe first, from my understanding, can you go to the first slide that you showed with cycle counts? That was slide 12 or 11. So the one before. So no, one earlier, that one. So what I was wondering is, you have the cycle counts for the Murex, and then you have the cycle count for sparse mole, and they're essentially, are they just the same, or?
Yes, because for QTesla, you don't have sparse polynomial multiplication operations for key generation. That's why, for example, even if you add a sparse polynomial multiplier to the Morex SoC, you don't bring any performance changes to the key generation. But you can see that there is a change, for example, for the signing and also for the verification. Yeah. Okay,
so now I understand how to read these tables. Thank you. Yeah. The second question was, so at the beginning, you just looking if there's other questions popping up. There's now something in the chat here. Should maybe go for those first.
No, there are questions. There are questions.
Yeah. So there's now some popping up here. Could you, so to everyone, if you don't mind posting it to the Zulip chat, that would be much easier to keep an eye on then. Okay, so there is one question how this work compares with the generic Sapphire PQC crypto coprocessor from MIT.
Oh, yes. So I actually previously had one comparison slide, but I removed it due to time constraint. So our work, one of the important design decision is we want to base our software co-design on a standard processor model. The Sapphire work is based on a customized processor. Basically, their hardware accelerator is closely coupled to a custom processor. While in our work, you can take the ARM processor, you can take the RISC-V, and then for all the bridge modules, for all the hardware accelerators, you can easily port it from one platform to the other. I don't think you can easily achieve that for Sapphire, but you target different applications for different processor models.
Okay, and then there's one more question asking which FPGA did you use and would you optimize differently for ASIC?
We used RTX 7, this AC701 FPGA. I think this is the FPGA recommended by NIST for prototyping PQC algorithms. We didn't really do any FPGA specific optimizations. I think you definitely can do some, take advantage of the DSP units or etc. But we don't really do that because we want to make sure that the design is generic enough to be able to run on different platforms, including different FPGA platforms.
Okay, and then so I have one last question if I don't see anything else popping up. So at the beginning you said that you want to have an architecture that is rather flexible and can handle different parameters and different schemes.
Yeah.
So I was wondering in your NTT implementation, so if you look at say lattice-based chems versus lattice-based signatures, and then in particular the provable parameter set of Q Tesla, the size of Q is quite different, right?
Yeah.
So now, of course, you need to have some sort of multiplier that can handle the biggest Q that you care about. But can you at all does it at all become more efficient if it runs on a smaller Q?
So basically, there are two types of hardware designs in terms of being parameterizable. You can either tune the parameters on the runtime. I think one of the work from just 2020, this software hardware co-design for SAIC was one of this type of work. But for our design, basically, you cannot change the parameters on the fly. You can set your parameters at synthesis time. Basically, choose the parameters and they generate the specific set of parameters, the design for you, basically.
Okay, yeah, that makes it clear. Thank you.
Yeah.
I think we should postpone further questions to the end of the session if we still have time, and then continue with the next talk. Thank you very much again.
Thank you.
Thank you for the presentation. So we're going to have the third talk of the session, which is Cortex M4 optimization for ring and module LW scheme. And Yusuf Alper Bilgin is going to give the talk. So Yusuf, if you can share your screen. Hello, Yusuf Alper Bilgin. Are you here? Oh, good. Thank you.
Yeah, please unmute yourself.
Because of my internet connection, I think I didn't hear you before. This is a joint work with Erdem Alkım, Murat Cenk, and François Gerard. Our paper proposes various optimizations for lattice-based key encapsulation mechanisms using the number-theoretic transform, NTT, on the ARM Cortex M4 microcontroller. So our target algorithms are Kyber, NewHope, and NewHope Compact, a faster and smaller variant of NewHope. So we have three similar NTT implementations running on different rings. As you can see, we have some different rings, 6 different rings, but they are very similar. So let me move on to our contributions quickly. We present a more efficient model reduction algorithm, which we need heavily during our computations. This is a Montgomery reduction. The one on the left side is implemented in 3 clock cycles. In this work, we optimize the implementation of this Montgomery reduction such that it can be performed in only 2 clock cycles. We achieve this by storing minus q to the minus 1 instead of q to the minus 1, and using sign, multiply, and add instruction, which multiplies two half words and adds the 32-bit results to another 32-bit value in only one clock cycle. So this improvement might look slim at the first sight, but Kyber performs 3,200 Montgomery reductions in a full polynomial. So we save 3,200 polynomial clock cycles for a full polynomial multiplication. So Cortex-M4 comes with restriction of limited number of registers, which is 16 general purpose 2-bit registers, out of which only 14 are available for the developer. In this work, we load 2 coefficients into 1 register. In total, we have 16 coefficients in only 14 usable registers at once, and perform 4 layers of NTT depending on the distance between the coefficients being used in the same butterfly. In other words, we load coefficients into these registers in such a way that a maximum number of entity layers can be performed before storing the results. So it is common that the optimized NTT implementations heavily use lazy reduction to speed up the code. However, those lazy reductions are mostly performed after an addition or subtraction. In this work, we also perform lazy reductions during component-wise multiplication. Here is an example. As you can see here, we can skip the intermediate reductions and perform a modular reduction at the end instead. Note that the Q value here is below 12-bit and while our architecture is 32-bit. So this multiplication, A0.B1, is below 24-bit, way lower than 32-bit. We can also skip the Montgomery reductions after the multiplications in the first layer of entity, where the inputs are polynomials with small coefficients that are sampled from the centered binomial distributions, usually the secret term S or the error term E. We also optimize small degree polynomial multiplications for NewHope and Kyber, NewHope Compact and Kyber. So another contribution is reducing the stack usage. NTT is already stack friendly. It is entirely in place. In this work, we reduce the stack usage of key generation algorithm by adding the error term on the fly. Instead of computing the first equation, we compute the second one. So the first equation needs at least 2 polynomials, S and E on the stack to compute the entity of these polynomials. However, the second one only needs S on the RAM, and we can compute A dot entity of S on the fly. Then we take the inverse entity of this result. Then we can add the error term on the fly as well. So at the cost of one more inverse entity, the stack usage of key generation is decreased almost 1 polynomial. So the trade-off between secret key size and decapsulation speed. This is actually a well-known idea. There are different options. We choose to store only the 32-byte seed used to sample the secret key. Then during decapsulation, we sample the secret key again and transform it to entity domain. This obviously reduces the secret key size, but increases the decapsulation time. Also, one important note is that we implement these last 2 optimizations in a modular fashion so that they can be enabled or disabled very easily. Moreover, we give a unified framework to compare Kyber, NewHope, and NewHope Compact as they use the same level of optimization. This table represents our cycle count comparison. As I told before, we can easily enable or disable stack optimization or the trade-off between secret key size and the decapsulation time. So we have 3 columns here: speed, stack optimization, and the short secret key. One can see that NewHope and Kyber perform around 10% better with our optimizations. Furthermore, NewHope Compact is more than 40% faster compared to NewHope and 25% faster compared to Kyber. The stack usage comparison in bytes is given in the slides. Our results for NewHope are less than half of the previous implementation. We also improved the stack usage for Kyber. As you can see, the most improvement is spotted on the key generation, thanks to our stack usage optimization for the key generation algorithm. In this slide, you can see the cycle count comparison for the polynomial multiplications functions, entity, inverse entity, and coefficient-wise multiplication. it can be seen that Kyber and NewHope Compact have similar performances while NewHope is slower. This is mainly due to the extra layers of the NTT and the increased number of reductions caused by the larger modulus. It can also be seen that our implementation of NewHope NTT is slightly slower while compared to the previous implementation, while we have noticeably better performance for the inverse NTT. So there are still some rooms for the improvement. One interesting point is that actually I just mentioned it before, our NTT implementation for the NewHope is slightly slower than the one reported before. The difference between them is that we use Kuleitaki butterfly for the forward entity. However, the previous implementation uses Gentleman Sunday. So using Gentleman Sunday for the forward entity for NewHope might improve the performance at the cost of storing more trivial factors. And representing coefficients as 32-bit signed integers instead of 16-bit might improve performance. By doing so, we can be even more aggressive with the lazy reduction at the cost of using more registers. So you can reach our source code on this GitHub link. Thank you for listening.
Thank you very much. Again, I don't see any questions in the chat, but I have one question. We're also running slightly over time. So first of all, really cool work. It's great to see how much faster the NTT became. But my experience is that when optimizing the NTT for schemes like Kyber or NewHope, it's in a way a bit of a frustrating experience because you put all this effort into making the NTT faster, and then you integrate that in the whole scheme, and then Ketchak happens, and actually Ketchak takes what, 80% of the cycles. So could you comment on that? Like how important is it, say, for people to keep looking at faster NTTs if in the end all the cycles are being spent on Ketchak?
Yes, actually I agree. At the end, we see the Ketchak performance because the most of the cycle count will be Ketchak, actually, 80%, as you mentioned. But I am not sure, but maybe we can see Ketchak improvements later for the other architecture as well, not just for this one. And actually, we have another table for the polynomial multiplication comparison and entity comparison for Kyber and NewHope. And I think that is more important than the whole scheme. So because at the end, Ketchak will improve for all of them.
That is true, yes. If we get hardware acceleration, for example, then yes. That's true. Okay. So I'll keep an eye on the chat and see if more questions are popping up. Maybe we can have them at the end of the session. Until then, thank you very much again. And then I think we should continue with the next talk.
Thank you for the presentation. So let's continue with the next talk. So we're gonna get away from NTT a little bit, and we're gonna talk about time memory trade-off in Tom Cook multiplication and application to module lattice-based cryptography. And Jose Maria Bermuda-Mera is gonna give the talk.
Okay, yeah, hi everyone, and thank you for being here. I'm going to briefly introduce our paper, Time Memory Trade-off in Tom Cook Multiplication, an application to lattice-based cryptography. That is a joint work with Anshuman and Ingrid. And hopefully after this small talk, you will want to know more details and read our paper or watch the long video. Yeah, I will briefly introduce the context of this work, and I will just summarize the contributions. I will not show results in this presentation, but you can check them out on the long video or on the paper. I will finish with some conclusions, and then we will have the questions and answers. Yeah, the context of this work is the NIST standardization context for post-quantum cryptography. And if we look at the finalists for this contest, we can see that lattice-based schemes are the most promising solution. But moreover, within lattice-based schemes, module lattices seem to be a preferred choice because of their better performance and the trade-off between security and performance. And when implementing module lattices, we have, rather than a big matrix vector multiplication, we have a polynomial arithmetic a small matrix vector multiplication of polynomials. So what we want to focus is on polynomial multiplication. The two approaches for polynomial multiplication are the coefficient multiplication, also called the school books, and it has a quadratic complexity. And then we have the most efficient method for polynomial multiplication, which has a linear complexity, and it's based on the point value representation of the polynomials. So there are different methods to go from one domain to the other. And the most commonly used in cryptography are the NTT, as it is used in Kyber and Dilithium, and Karatsuba-Dumcook, which is used on Saber. And we focus on optimizing Karatsuba-Dumcook within the context of module lattice-based cryptography. And why I said within the context of module lattice-based cryptography is because we don't really perform a single polynomial multiplication, but this is small matrix vector multiplication. We have here an example with dimension 3. And we take advantage of the fact that we don't really need to compute all the polynomial multiplications, but we just care about the result. And then we propose these two techniques, Lattice interpolation, where we take advantage of the fact that we don't need the intermediate results, but just the addition. So we can perform not only the multiplication in the point value domain, but also all the additions, and save up the number of interpolations at the expense of a larger memory. And for pre-computation, we take advantage of the fact that one of the operands, in this case the secret, is we reuse for every row column product. So we can again evaluate all these polynomials and store them in the point value domain, trading off time for a larger memory utilization. In our paper, we discussed the implications of these optimizations when implementing them in different platforms. And one of the conclusions is that for embedded systems, this memory overhead would be quite large. So instead of a speed optimized version, we propose a memory optimized version of Saber for embedded systems. And here, first we realized that when storing the secrets, instead of using 13 bits per coefficient, since we are sampling the secrets from a binomial distribution, we could really shrink the number of bits that we use for each coefficient. And this will reduce, of course, the footprint of the secret keys, but it will also simplify the packing and unpacking of the secrets into a bit string. And moreover, we can embed these packing and unpacking functions within the evaluation routine for the multiplication. And yeah, we also propose other memory optimizations like just-in-time polynomial generation, in-place ciphertext verification, etc. And yeah, as a conclusion, so in our paper we have formalized and generalized Lattice interpolation and pre-computation. We have shown how these theoretical optimizations can have different implications depending on the platform on which they are implemented. And we also provide the fastest software implementations for Saber in the state of the art. And alternatively, for embedded platforms, we provide the smallest Saber implementation and also the reduced storage for the secret keys of Saber. Besides our paper, you can also check out our source code on GitHub. You can find the link on our paper as well. Yeah, that's it. Thank you for your attention, and I'll be glad to answer your questions now.
Thank you very much. And this time I actually do have some questions here. So there was one question popping up in the Zulip chat asking if isn't Andrew and Falcon also based on polynomial arithmetic?
Yeah, so Andrew also has polynomial multiplication, but it's not really module lattice, it's ideal lattice scheme, or well, Andrew is not considered a ring problem, but it's kind of its own type. And they have a single polynomial multiplication. They don't really have this matrix vector multiplication, so they couldn't take advantage of the Lattice interpolation or the pre-computation.
Okay. Another question that somehow went only to me. will pre-compute and store the secret, pre-computing and storing the secrets leak more side channel information?
Well, actually, that's I would disagree with that statement, because actually when we use 13 bits instead, let's say if we have a binomial sampler that produces coefficients that effectively have 4 bits of information, let's say between -5, when we store that value as a 13-bit value, what we are doing is sign extension of the most significant bit. So yeah, this sign extension can be done on beforehand and then store it already with the sign extension. Or what we do is we do it in runtime when unpacking these secrets from the bit string. And yeah, I wouldn't say there is more leakage, but moreover, I would say there could be potentially more leakage on the previous approach, because if you get to read 1 bit of the memory that turns out to be, let's say, the 10th, 11th, 9th most significant bit of this coefficient, then automatically you know all the bits that are equal to that because of this sign extension.
Okay.
So it's a more compact storage.
Okay, thank you very much. For the moment, I don't see any further questions, but as for the other talks, I'll try to keep them collected. And if there's more popping up, let's see how much time we have at the end of the session. So okay. Yeah, thank you again very much. And then I think we continue, and I hand over to Tom Fred again.
Thank you for your presentation. It was really interesting. So we have 2 more presentations in this session. So the next one is about high-speed instruction set coprocessor for lattice-based key encapsulation mechanism, Saber in hardware, and Andrea Basso is going to give the talk.
Hi, everybody. Thank you for the introduction. Can you all see my screen?
Yes, that's perfect.
Great. So in the interest of time, allow me to do things a bit in reverse and start from the conclusion. In our paper, we propose a complete hardware architecture for Saber that could compute all 3 CAM operations, key generation, encapsulation, and decapsulation, and could target all security levels of the Saber protocol, Live Saber, Saber, and Fire Saber. And the proposed architecture can achieve very high levels of performance. And indeed, it does outperform previous implementations of Saber in hardware, in some cases even by several orders of magnitude, and it does outperform the vast majority of implementations of other post-quantum algorithms. And it does this while still remaining highly flexible and only with a moderate error consumption requirement. Moving beyond Saber, we also propose a generic framework that can be used for other lattice-based protocols, and we demonstrated that it's possible to achieve high levels of performance when computing polynomial multiplication, even using a non-NTT-based polynomial multiplier. Why is this important? Saber is now one of the 4 round-tree finalists for the NIST post-quantum standardization process. And according to NIST itself, Saber is one of the most promising schemes. So investigating the hardware implementation of Saber was certainly an interesting research topic. Moreover, Saber has some unique characteristics that make its hardware implementation requiring a different approach compared to other lattice-based protocols. And in particular, we were interested in investigating the performance of non-NTT-based polynomial multipliers, because Saber does not allow the usage of NTT. And at the core of our implementation is the multiply and accumulate unit used in polynomial multiplication. Indeed, we decided to focus on polynomial multiplication because that was the main performance bottleneck. And we exploited the unique characteristics of Saber to develop a multiply and accumulate unit that could be implemented with very little area. Indeed, Saber has small secrets. All the coefficients of the secret polynomials lie in the range -3,3, -4,4, and -5,5, depending on the security level. So we could implement coefficient-wise multiplier between a full 13-bit number and a small secret, only using bit shift operations and additions. Moreover, Saber uses power of 2 moduli. Indeed, all coefficient-wise operations take place modulo 2 to the 13th or 2 to the 10th. So there was no need for a dedicated circuit for modular reduction. And that meant that combined with the small secrets, we could implement a full MAC unit with only 50 LUTs. And given the small area consumption, we could parallelize several of them. And this is the architecture for our polynomial multiplier, which implements the school book algorithm, the classic algorithm for polynomial multiplication, where you can see there are several 256 MAC units in parallel, each one connected to one coefficient of the secret polynomial. And that means that each cycle we can compute the multiplication between one coefficient from the public polynomial with all the coefficients of the secret polynomial. And by doing this, we can compute a full polynomial multiplication in only 256 cycles. Moreover, we also introduce a framework to target all performance area trade-off levels. And to demonstrate it in practice, we implemented a variant of this polynomial multiplier that can compute a full multiplication in only 128 cycles. Let's now see the overall results. We implemented our architecture on an UltraScale Plus FPGA, and we saw that key generation requires less than 22 microseconds, encapsulation less than 27 microseconds, and encapsulation about 32 microseconds, which is a very high level of performance, and it also gives us a very high throughput. If you look at the breakdown, you can see that polynomial multiplication does require the majority of the time, about 50% of the computation time, whereas catch-up requires about 1/3. And we were able to achieve this high level of performance while still maintaining a moderate error consumption. Indeed, our architecture only consumed less than 9% of the LUTs available and less than 2% of the flip-flops available on the FPGA. Moreover, our architecture does not use any DSPs at all and only 2 BRAM tiles. And given the moderate error consumption, it is actually possible to fit up to 11 coprocessors on a single FPGA, which would give an incredibly high throughput. So overall, our architecture can maintain a moderate error consumption while still achieving very high levels of performance. Thank you very much for your attention.
Thank you very much for the very nice talk. So far, there's no questions in the Zulip chat. There's actually, okay. There's a question now asking, do you see opportunities of using Karatsuba to improve the speed instead of schoolbook multiplication?
Yes, well, the thing is that this kind of polynomial multiplier is much simpler to implement than Karatsuba because the recursive nature of Karatsuba make it more complicated in hardware since each level would require a dedicated implementation. So using a schoolbook is simpler to implement and it is more flexible. But it is possible, and I believe that only 2 weeks ago, hardware implementation of Saber using the Karatsuba method has been posted to the ePrint, so it is definitely doable. But there is a trade-off between like performance and simplicity and flexibility.
Okay, then I have one more question. So I think most designer teams, when designing the schemes for the NIST competition at first, well, they had performance in mind, of course, but then first implemented things in software. And then only later people picked up and actually implemented those schemes in hardware. And I was wondering, while implementing Saber, did you at some point stumble across some design decision where you felt like, oh, if you had just done this one detail slightly differently, my life would be so much easier? Something that we can all learn from maybe in designing those schemes.
Ooh, that's an interesting question. Well, I guess, for instance, well, the fact that like modulo 2 or like the moduli were power of 2 overall was really convenient. I think one thing that wasn't as convenient, for instance, was the fact that the coefficients of the public polynomial are 13-bit long. And that means that it does not work well. It does not divide 64. So like these coefficients, when stored in the BRAM, are stored across different blocks, and that created quite some problems. overall. So I think using both when like in the size of the coefficients, but also like in the binomial settings, using numbers that easily divide 64 does make implementation much simpler.
Okay.
So that would definitely be one thing. Yeah.
There's one more question popping up in the Zulip chat. Do you have results comparing using your polynomial multiplier with a scheme that uses NTT like Kyber?
We don't have specifics like concrete results, but for instance, I think, well, so we did propose a variant of this polynomial multiplier that implements the coefficient-wise multiplier with DSPs and modular reduction. And of course, that requires much larger area consumption. But yes, I mean, I think one of the main key points of this was that like we wanted to exploit the fact that we could get away without doing modular reduction because we were using power of 2. So for instance, already implementing Kyber would be already quite different. But also I believe that Kyber has the NTT multiplication embedded into the protocol itself. So it's actually not possible to use a non-NTT based polynomial multiplier unless
you do something
because like it does, it's at least like, or at least it wouldn't fit the protocol itself.
True. Yeah. All right. I don't see any further questions. So in that sense, thank you again. Very nice presentation. And I think we can continue with the last talk of the session.
Thank you for the presentation. So this is the last talk of the session. Then there will be a 20-minute break before the keynote. So this talk is RISC-V, tightly coupled RISC-V accelerators for post-quantum cryptography. And Tim Fritzman is going to give the talk.
Yeah, so thank you very much for the introduction. Can you see my slides?
Yes.
Okay, perfect. So I will present RISC-V, which was a joint work with Georg Siegel and Joanna Sepulveda. So ideal lattice-based cryptography has usually two performance bottlenecks: the ring arithmetic, in particular the polynomial multiplication, and the sampling of random polynomials. And in order to increase the efficiency of software designs, hardware-software co-design strategies can be used. So we have two different types of accelerators that we can choose for our co-design. Loosely coupled accelerators have the advantage that they can be easily integrated into the system, for example with an AXI bus, and they are in particular efficient for large tasks with a low data transfer overhead. Therefore, often they implement the whole cryptographic scheme, or at least large parts of it. In contrast, tightly coupled accelerators do not have a complex bus communication and are also suitable for smaller tasks. This makes them an ideal candidate for developing highly flexible, but also small area solutions. While loosely coupled accelerators have already attracted a lot of attention, tightly coupled accelerators have received less attention, and only a single work uses the advantages of a tight coupling in order to create a tightly coupled finite field accelerator, accelerating single field multiplications, additions, and subtractions. However, in this work, we present more powerful tightly coupled accelerators and also accelerators for all the performance bottlenecks of ideal lattice-based cryptography, including the sampling and hashing. So the polynomial multiplication can be accelerated using an NTT-based or an Karatsuba-based approach. For the NTT-based schemes, we developed the entity and modular arithmetic unit. It basically consists of three different parts: an address unit, a twiddle update unit to reduce the amount of pre-computations, and a modular arithmetic unit, which is capable of performing vectorized modular multiplications, additions, subtractions, but also complete butterfly operations as well as further entity operations. For the Karatsuba-based schemes, we developed the Pico-Mac operation, which is basically a vectorized modular multiply accumulate function. We can use for both of our accelerators a vectorized approach because the additions, multiplications, and subtractions, the results can be reduced to a half word. And this allows us to use a vectorized approach or SIMD principle. Now, the second performance bottleneck of ideal lattice-based cryptography is usually the sampling, which can be accelerated using an Ketchak accelerator. Previous Ketchak implementations couple the core either to a bus system, for example, an AXI bus, or to a 32-bit system memory interface. Now, in this work, we couple our Ketchak accelerator directly to the general purpose and floating point register set. And this allows us to have a completely parallel access of the full Ketchak state. And instead of implementing the whole cryptographic algorithm, we accelerate the performance critical operation, which is one round of the Ketchak round permutation. Now, in order to turn the uniform samples into binomially distributed ones, we present the binomial sampling unit. It is basically a modular subtractions of several Hamming weights, and it supports several variances. We integrated then our accelerators directly into the RISC-V core, which was a 32-bit inline processor. Moreover, we developed design strategies how to reuse existing hardware resources and how to decrease the access to the main memory, which increases in turn the performance. To summarize this work, in this work we present RISC-V, an enhanced RISC-V architecture that integrates powerful tightly coupled accelerators. Moreover, we developed instruction set extensions for the modular arithmetic, but also for other performance bottlenecks, such as the Ketchak and the binomial sampling. When comparing the cycle count of the latest Cortex-M4 implementation, the RISC-V-based design using a tightly coupled finite field accelerator, and our approach, then we can see that for NewHope and Kyber, we can achieve a clear cycle count reduction. And also for Sabre, when compared to the baseline implementation, we have a clear cycle count reduction. So this summarized my work, and thank you very much for your attention, and I'm happy to answer any question.
All right, so thank you very much. Very nice presentation. There are actually questions popping up, so I'll just read them out here. So one question is, does your design include the entire floating point unit in the design? Do you only include the FP registers? If the FP unit is included, how big is it in comparison to the rest of the design?
Yes, actually, in this work, we only included the floating point register set and not the whole FPU.
Okay.
When we compare the overhead of the plain RISC-V core and our work, then for our ASIC implementation, we have a cell count increase of factor 1.6.
Okay, thank you very much. Next question is, why do you use the floating point registers for your architecture and apparently non-related floating point, non-floating point related tasks? Why not create a separate set of registers and call it PQ registers?
So to answer this question, we want to reuse existing hardware resources, and why to duplicate an available register set. So we will not use our floating point register during the, for example, the cryptographic computation, and therefore we can simply use what is already in the design. So this was the general idea. But of course, we could also spend another register set for this.
Makes sense to me. Thank you very much. There's one more question. I mean, obviously the Ketchak part of the work is interesting quite a bit beyond, well, the lattice-based schemes that you've been looking into. So I was wondering, is it efficient for basically any input length? Is it optimized for like long inputs, long outputs? Is it what's the latency of the Ketchak would it be, for example, be useful to accelerate hash-based signatures?
Yes, so it is really a general accelerator which is usable for all the schemes. And for example, when using it for NewHope and Kyber, then we can see that we can already get to a lower clock cycle count when compared to the latest Cortex-ARM4 implementation. For Saber, there's not so much randomness. For example, the rounding makes a lot of randomness that we do not have to accelerate. The latency of the Keccak implementation is 1 clock cycle per state permutation. And our design strategies is really to hold the state completely within the register set. And for the whole sampling process, for example, and simply permute the state again if we require fresh randomness. So this eliminates all the load and store operations to the system memory and improves the performance a lot. So we are really flexible. We can, yes, kind of doing all the Keccak functionalities with this design.
While you were answering this question, several other questions popped up. And so one question was, you hook into existing registers, so the floating point and the general purpose registers. Does this reduce the frequency of the rest of the core?
So I did not have a really close look, but you only need some multiplexers before the register sets. And yes, of course, they will have a low influence, but not a really large influence. Now the bottleneck in terms of frequency is more in the in the NTT unit, which would, for example, could also use some pipeline registers in order to improve the frequency here.
Okay, so we're slightly running over time, but there's still one question that I think concludes the session very nicely, namely if you would consider contributing your work to the RISC-V Foundation for Standardization.
That's a good idea. So actually, yes, we should think about this. And I think it makes sense to, yes, keep in touch with them. And also as far, so when the competition goes more and more to the end, then it's getting more and more interesting also for the RISC-V community, of course.
Yeah, so you might want to then get in touch with Helena Hanschu, who asked this question and who I think knows this really well. So I think I would delay further questions to the chat. So the chat is still ongoing. So if you have more questions, please post them there and then maybe authors can answer. And I think, well, that pretty much concludes the session. So thank you to all speakers from my side. And well, I guess see you soon in the social event and in the invite.
Thank you very much, everyone.